Okay, here's an example to help us finally work through mathematically some Newton's law problems. We have a skydiver who's in free fall, so she's jumped out of the plane, she's falling freely. Then she deploys her parachute, which results in a drag force of 800 newtons. Calculate her acceleration before and after parachute deployment. We are going to have to make some assumptions to make this problem simpler for us, so we'll talk about that. The first thing I want to do is think about the question that's being asked of me. I have a skydiver. I know her mass. Remember, that's how much matter the skydiver has. That's her inertia. It's not her weight. Remember, those are different. And I know she's falling. She deploys her parachute. The parachute results in a drag force. And I'm asked to find something before and after that parachute is deployed. So I think I'm going to have to do two separate calculations, two separate problems to solve. And for every single force problem that you solve, you have got to draw one of those force or free body diagrams. So let's say over here to the left, I'm going to start out with a diagram of the skydiver, which I'm going to label with an S in free fall. So let me think about all the forces acting on the skydiver. Is there anything pushing her left and right? I mean, maybe a little bit if there's some wind, but we're going to ignore that. The biggest force you should be thinking about right now is the force of gravity going down. I'm going to call that F of G. And yeah, you could label it force of gravity felt by the skydiver, dealt by the earth. You can do that if you want to, but I'm not asking about any third law pairs or anything like that. So to save time, I'm actually going to not worry about that. Is there any force acting up on her? Well, yeah, there would be, even though she hasn't deployed her parachute yet. I'm looking at the before. Even though she hasn't deployed that parachute yet, there are still air particles and things like that colliding into her and pushing her up. But I'm going to ignore that. I'm going to ignore that air resistance. She's in free fall. The biggest force affecting her is going to be this force of gravity. I want to know, what is her acceleration right now? So do I have some tool, some equation that can help me find acceleration? Whenever you're solving these problems, in fact, whenever you're solving most problems in any science classes, you're going to follow a very set series of steps. The first step is always going to be to model your scenario and make a list of things that you know. What do we know from the problem that I could add to my diagram? Well, I know that the skydiver has a mass of 67 kilograms, right? So I could label that on my diagram. And now I'm going to write down what I do not know. What is her acceleration going to be? So A equals question mark. That's what I'm trying to find. And then I'm going to think to myself, do I have any concept, any law, any equation, any tool in my science utility tool belt that can help me solve for that unknown? Anything that relates what I do know and what I don't know, so I can make an equation and solve? And the answer is yes. For any of these problems, our known equation is Newton's second law. The sum of all of the forces acting on the object equals the object's mass times its acceleration. I have the mass of the object, 67 kilograms, so if I can put a number over here to the left for the sum of all the forces acting, then I can find the object's acceleration. I can solve. It's going to be simple algebra. So let me think about all the forces acting on this object. All the forces acting on this object, there's just one. It's simple, the force of gravity. Well, is there a way for me to calculate the force of gravity, to turn that into a number, to figure out how strong is that force? Well, yeah, there is. You guys know from our discussion earlier that the force of gravity is, near the surface of the Earth is always m times g. G is, do you guys remember the number? 9.8. 9.8 is not the force of gravity, but is rather little g, the acceleration due to the force of gravity. So I can calculate the force of gravity right now, 67 times 9.8. There may be some practice problems, example problems that have you round that 9.8 to 10, but I hate to do that. It's a pet peeve of mine for some reason. So 67 times 9.8, getting 656.6. What's the unit? Newtons. So that is the size of the force of gravity acting on her. In what direction is that force going? Remember, forces are vectors. They have a directional component. It's pointing down. You can consider down to be negative or positive. It really does not matter to me. I like to consider down to be negative because it's going uh, down. The skydiver's height is decreasing, so to speak. So I just need to remember that, hey, this is down, this is negative. So I'm going to call that a negative 656.6. So now I know the sum of all the forces. If I add up all the forces acting on this person in one direction, it's right here. It's that number, negative 656.6 equals MA. Well, do I know what the mass is? Yeah, I do. I can plug that in. 67 kilograms. So you'll see I get negative 656.6 equals 67A. How can I solve for that A, that unknown variable? How can I solve this problem? Easy enough, just divide both sides by 67. I think you can see already that we kind of took a long way of doing this. It's exactly what we did down here. Negative 656.6 equals the mass times 9.8. Well, guess what? The acceleration here is going to be negative 9.8 meters per second squared. She's moving in a downward direction. Her acceleration is negative. She's accelerating down, speeding up, getting faster and faster as she falls down to the surface of the Earth. Negative 9.8 meters per second squared. I really could have skipped this step right here. I could have recognized, oh, the only force acting on her is the force of gravity. And I know that the acceleration due to gravity near the surface of the Earth is little g, which is 9.8. And we said it was negative because we're considering down to be the negative direction, and that force, that acceleration, is down. So there's the answer for the first part, her acceleration before her parachute deploys. This would have been our answer no matter what the mass was, no matter what the object was. If it was a hammer, a rock, a feather, we should have gotten 9.8 meters per second squared. Now, how come whenever you drop a hammer and a feather on Earth, they both don't accelerate downward at 9.8 meters per second squared? You know the feather will fall more slowly. Well, it's because the feather is feathery, and it has a lot of surface area to kind of interact with and collide with the air particles. So as the feather falls, it's more spread out, it's more feathery. Evolution kind of designed it that way to collide a lot with air particles, so that upward air resistance is going to slow it down. Remember, in this question, we're not worried about air resistance until after the parachute. So for our purposes, because we usually ignore air resistance, anything that falls is going to fall near the surface of the Earth with an acceleration of 9.8 meters per second squared and down. Let's now solve this problem after the parachute has been deployed. So once again, I'm going to follow the exact same problem-solving guidelines. I'm going to make a list of everything I know, and I'm going to model the problem. Here's my skydiver. Her mass is still 67 kilograms. I know this seems redundant, but it really is the most helpful thing you can do to solve these problems and make sure you don't forget anything. Is to make is to create a well-made, very accurate model and make a list of everything you know. So the forces, obviously the force of gravity, that's the easiest one to consider. We can go ahead and give a number to that. We know it's equal to mg. And we've already calculated that over here. Again, we said that down is negative, so negative 656.6 newtons. Are there any other forces acting on the skydiver now after the parachute has been deployed? Yes, there is. There is a drag force of 800 newtons. What direction is that going to be in? It's going to be up. That's dragging, pulling the parachuter up. So I'm going to call that a force of drag. You could call it force of air resistance if you want, equals 800 newtons. Now I think you're going to see how we can answer the question for this problem. What is the acceleration? Is the acceleration going to be 9.8? Again, is she still under only the influence of gravity? No, we have this other force to consider. I've listed everything I know. I listed what I did not know. And then I'm thinking, do I have a tool to help connect those, to bridge the gap Yes, I do. I have Newton's second law. So I'm going to write that down, and I'm just going to start filling this out so I can solve for that unknown variable. Let me show you what to do with this left-hand side, the sigma F. Remember, that means the sum of, or the total overall force. That just means to take all your forces that are acting in the same dimension, and by that I mean the vertical dimension, the vertical axis up and down, and add them together. These forces are opposing each other. So I'm going to take my 800, and it's positive. Remember, forces are vectors. We said earlier that this downward force is going to be negative, so the upward force has got to be positive. Positive 800. What does the sigma mean? It means total, sum, add up. So 800 plus my other force is negative 656.6. That is the left side of this equation, the sum of all the forces. I've just expanded it to do what the equation tells me to do, add up all the forces. 800 plus a negative is going to be 800 minus 656.6. And I am trying to solve for this a value, so I need to collapse this left side of the equation into just one number. So that's what I'm going to do right here. 800 minus 656.6 is going to be 143.4. Is that my acceleration? No, that's the size of the net overall force. Basically what I've done is I've said, okay, there's a downward force of 656.6. There's an upward force of 800. And what I've done is I've seen what is the difference here. How much bigger is that upward force compared to the downward force? And I saw that it's 143.4. That is the overall total force, the overall sum of the forces. You'll see that these forces are not balanced. So I am going to have an acceleration. So I found the sum of the forces, 143.4. So I can say now that 143.4 equals the mass times the acceleration. And I know what the mass is, don't I? Her mass is still 67 kilograms. And so now you can see I'm one step away from solving the question, how do I solve for the unknown variable A? I divide both sides by 67. That goes away. So I'm going to get A equals a number. And the answer I got is 2.14. And it's positive, 2.14 meters per second squared. How is that going to change her motion? Well, in what direction was she falling? She was falling in the downward direction, the negative direction, so she had a negative velocity, some negative velocity, and now she has a positive acceleration. So what's she going to do? She's going to start slowing down all of a sudden, and her velocity will approach zero, and she may even change direction and get pulled upward. So she's going to slow down, which is exactly what we want. The acceleration is positive, the velocity is negative. She's going to slow down. To summarize, the first step is make your model, draw your force diagrams, label everything you know about the object. I labeled the mass. Label all the forces acting on the object and everything you know about those forces. I knew the force of gravity is m times g, so I worked that out. I knew the drag force was 800. And then write down what you don't know. In both cases, I was solving for the unknown acceleration. And then see if you have a tool that connects everything. And it's this Newton's second law. In this question, it was quite easy. The acceleration is just little g, the acceleration due to gravity. I have no other forces. This problem is more complicated. I have a downward force and an upward force. So I had to find the sum of those. Forces are vectors, so I have to consider the direction, positive 800 going up, plus a negative 656.6, that force of gravity going down. That gave me a net force of 143.4, just like I said up here. Is that the acceleration? No, that's just the net force. So net force equals mass times acceleration. Plugged in 67 for the mass. Here's my missing variable, my unknown acceleration. And then just solve the algebra.